Suppose you have a physics problem, and the problem looks like this. Two blocks with given masses slide on a frictionless surface toward each other with given velocities. If they collide elastically, what are their velocities afterward? How do you approach this problem? What do you have to lean on? Well, a couple of things come to mind. These two pillars of physics depend on certain conditions, so before we launch into things, we'd best check if they're applicable. First, what permits us to appeal to energy conservation? Energy conservation depends on no work by non-conservative forces. Fair to say here? Well, there's no friction, so we're set there. Furthermore, we're told that the collision is elastic. That means that the forces of interaction between the colliding bodies are conservative. The potential energy stored in the moment of being smacked together is all returned afterward as the bodies spring apart again. How about momentum? Conservation of momentum requires no net external forces, or as it's sometimes said, a closed system. Gravity may act on the bodies in our problem, but normal forces do as well, and these two net out to zero, so we're all set to apply our two principles. Now, the traditional way to do this problem is to express the two conservation statements as mathematical expressions, starting with momentum. The total momentum before the collision is equal to the total momentum afterward, and the same can be said for kinetic energy. We take the numerical values from our problem, pop them into our math machine. Hey, look, a system of two equations with two unknowns. The first expression is linear, so we'll massage it to tell us one velocity in terms of the other. We can substitute this expression for v2 into the quadratic and get this. We'll square out the numerator and get this. Multiply through by a half. And now we should be able to make this look like a respectable quadratic by collecting all the terms over on the right. We divide through by the leading coefficient. Happily, we find, hey, Bob's your uncle, this factors neatly. Okay, so we can see two solutions. How do we interpret them? Let's look at the original system. The implied solutions tell us that if momentum and energy are to be conserved, that v1 can only have the value 1 or 3, and before the collision that value is 3. So we must infer that after the collision the velocity is positive 1. What about the velocity of the other block? Well, we can plug v1 equals 1 back into our momentum equation, and we find that v2 final is 6 meters per second. Okay, done. Nice. That's the traditional approach, but it's not the only approach. Here's an approach that only requires one quick calculation and drawing a few pictures. The first thing we do is find the velocity of the center of mass. This may seem like an odd thing to do, given that we don't know the block's location or where the center of mass is, let alone its velocity, but it turns out to be pretty easy to find. We know how to compute the position of the center of mass. That's the definition here, and VCM will be the time derivative of XCM, so we just differentiate both sides. I know I said this was the unmathy way to do this. You don't actually need to know this little derivation bit, so we'll just zip through. We break up the fraction to make it easier to differentiate, and we get two fractions with a bunch of constant masses, and yes, the x's become v's, and we can combine them into this thing here. And the terms in the numerator should look awfully familiar to you, so we'll just express the outcome this way. Okay, done with the math. We go back to our blocks now to perform step 1, the sum of the momenta over the sum of the masses, remembering that velocity to the left is negative, tells us that VCM is 2. Okay, now step 2. In step 2 we ask, what would this look like from the perspective of the center of mass? So now you should imagine yourself on a skateboard, zooming along next to our system at the velocity of the center of mass. How would the system look to you? Well, the green block would appear to be going faster than 2 meters per second, just like oncoming traffic. And the pink block would be slower than 3 meters per second, just like the highway traffic that's going your direction but at a different speed. If you imagine yourself to be stationary, which makes sense because compared to ourselves we are never moving, you might see things like this. The green block now comes at you at 4 meters per second and the pink at 1 meter per second. Now, if you don't want to have done this process by visualization, or maybe skateboards give you the willies because you once fell off your cousin's skateboard when you were 6 and you skinned your knee and spent the afternoon trying to pretend that it was all cool, even though things were not at all cool. But in any case, you can get the same result by computing the relative velocities. Each relative velocity is the original velocity minus the VCM, which is 2. And if you were wondering how the green block gets going at 4, which is to say, why am I claiming that 2 minus 2 is 4, then you should press pause right now and sort it out, because it's a thing worth thinking about. Step 3. Reverse the velocities. Seriously, just change their directions. This is the genius moment, the moment when we solve simultaneous equations just by looking at the picture in the right way. Why does this work? First, the laws of motion are supposed to work the same no matter what reference frame you use. Second, you have just created a symmetrical system. 4 at 1, 1 at 4, the total momentum is 0. If you flip the velocities, the total momentum is still 0. So you've just discovered one solution to the momentum conservation equation. Third, kinetic energy depends on the square of the velocity. So changing the sign of the velocity doesn't affect kinetic energy. You have also just magically found a new state for the system with precisely the same kinetic energy as the one you started with. Yes, Bob is your uncle. Now that we've done our magic, we have to go from the perspective of the CM to the way normal people see the system. We have to restart the CM to its original speed. The easiest way to do this is just to add positive 2 to all the velocities. That's it. You're done. In 4 simple steps, you have just taken a system and found a second state for it with the same total energy and momentum without solving no stinking quadratic simultaneous equations. Neat, huh? Oh, and by the way, the numbers all check out. Kinetic energy at the beginning is equal to kinetic energy at the end. Momentum at the beginning is equal to momentum at the end. Pretty sweet.